Okay, so first things first, I do want to revisit the last two. Okay, the reason why I want to revisit the last two on your salt table is because those are the most difficult ones. Those are the ones where we have to end up comparing some K values. All right. So the other thing that I wanted to try again today is I wanted to try to define salts again with like my fourth definition. So let's look at the bottom two. Let's look at the bottom two. Oh, there it is. Okay. Another way to define a salt. Okay. Now I'm going to try this one out for size. Like I said, I've kind of defined it like 4 different ways. The problem is the definition of a salt is saying that it's from acids and bases. So I'm kind of making a circular definition here. What I'm going to say is, if you can turn the cation, the first chunk, into a base, and you can turn the second chunk, the anion, into an acid, then you have a salt. Again, I know that's circular, but maybe that works a little better with your thinking. Maybe that works a little better with your thinking. So, NH4, we can make that into a base by taking away a hydrogen. It's ammonia. CN, we can make that into an acid by adding an H. It's hydrocyanic acid. Okay? Is this a salt? Yeah. Yes, it is. Is it part acidic? Yeah. This comes from a weak, the ammonium comes from the weak base, therefore it is part acidic. The cyanide comes from a weak acid, therefore it is also part basic. And if you remember from last Thursday, this is where we have to compare K values. All right, to figure out whether this salt is truly acidic or truly basic, we have to compare the acid strength of the ammonium with the base strength of the cyanide. So we need the Ka of ammonium and we need the Kb of cyanide. What's the Ka of ammonium? You should have that from last Thursday. 5.6 times 10 to the negative 10? Okay. What's the Kb, the base strength of cyanide ion? 1.6. That was the debate last week. 1.6 times 10 to the negative 5th. Okay. Which of those two numbers is larger? The Kb of cyanide, right? That's a larger number. They're both very, very tiny, but Kb of cyanide is larger. Therefore, the overall property of this salt is basic. This is going to win out. That has greater strength than this. So therefore, it's basic. The next one. Ammonium, we can turn that into ammonia, so we can make that a base. Acetate, we can definitely make that an acid. Just throw a hydrogen on it, we got acetic acid. So yes, this is a salt. Ammonium comes from a weak base, therefore it has acidic properties. Acetate comes from a weak acid, therefore it has basic properties. We got to compare K values again. And I know this is a refresher, but that's okay. They are equal. You look them up. Ammonium was 5.6 times 10 to the negative 10 for a Ka. The Kb of acetate is 5.6 times 10 to the negative 10. And what you get is they completely cancel each other out. Neither one is stronger than the other. Neutral. The question was asked last hour, how often does that happen? Very rarely. Very, very rarely. Okay? Because there's all sorts of K values. So this is pretty atypical. Okay, so let's move on. This is number 13 from your book. And I want you to think about, first off, what is meant by pH? Does anyone know what that actually stands for? Apart from pH less than 7 is acidic, pH greater than 7 is basic, pH 7 is neutral. So the pH measures the concentration of hydrogen ions. Okay, it's a measurement of that. That's a good guess. That's a good guess. It's a logarithmic scale. Does that help? P. P is for power. Power. Yeah, P is for power. So the term power is used with logarithmic scales. Okay, so we're going to see that little p in more than one place this year. We're actually going to see it probably later in the week when we talk about pKa and pKb, which are the power versions of Ka and Kb. It's pretty simple, don't worry. Okay. But what I want to show you, and what's really important about the pH scale, and I think we mentioned this last year, but I'm going to say it again this year, is if I have a pH of 7 and I have a pH of 6, okay, the pH of 6 is 10 times more concentrated in hydrogen ions than is the pH of 7. So this is 10x, 10 times more concentrated. 10 times more concentrated hydrogen ions. Okay. If I have a pH of 5 versus pH of 7, how many more times concentrated is the pH of 5? 100. Okay? We're stacking factors of 10. That's a power scale. That's what that P stands for. Okay? If I have a pH of 9 versus a pH of 7, my pH of 9 is 100 times less concentrated. So we kind of need a reference point. If you wanted to compare the concentration or the quantities of concentration versus one another and you're using pHs, you kind of want something to compare to. Normally we use 7, right? We use the neutral pH as kind of the baseline. Yeah, water. Okay? Water at a temperature of 25 degrees Celsius. If water is not 25 degrees Celsius, it actually is not a pH of 7. Which is a pain in the butt. We'll talk about that. Okay? Not ice. That's not what ice stands for. But. All right? So that's the important pieces about the pH scale that I want you to get away. True or false? A strong acid solution always has a lower pH than a weak acid solution. What do you got? What do we like for this one? Somebody raise a hand. Share what you got. True or false? Joe, what you got? False. Why?
Because when it says a strong acid, like a strong acid is just something that doesn't break apart a lot, but that doesn't define its pH.
You said it backwards, right? Strong acids break apart a ton? Yeah, I know what you meant. So strong acids break apart completely. However, this has nothing to do with concentration of anything. So I could have, for example, 0.000000001 molar HCl. Oops. Let's try that. And I could have 15 molar hydrofluoric acid. Okay? HCl is strong, hydrofluoric acid is weak. But my HCl is highly dilute, and my hydrofluoric acid is highly concentrated. So yes, every single one of these molecules will break apart and give me a hydrogen ion. Only a few of those are going to break apart. But I have a factor of like a billion, like 15 billion more hydrogen fluoride molecules than I do HCl molecules. So more of these, or I will have a greater concentration of hydrogen ions in that case. All right? What if they're equal? If I have a strong acid and a weak acid at the same concentration, which is going to have a lower pH? If I have, like we did last week in the lab, last Friday we did this. Okay? 0.10 molar HCl. 0.10 molar acetic acid. If you ran both of those titrations, which of those started at a lower pH? HCl. Does that make sense? Same concentration. They're both acids. Why does one have a lower pH? If we look at these two concentrations, okay, HCl started at a lower pH. You should have had a pH like right around 1-ish, right? Give or take. The acetic acid was somewhere above 3, like 3.2, 3.3, somewhere in there, I think. Okay? The reason is every single one of those breaks apart. So if we have 0.1 molar HCl, we have 0.1 molar hydrogen ions in solution. If I have 0.1 molar acetic acid, I have something else for hydrogen ion concentration. It's because some of them break apart, but not all of them. Okay? And most don't. So we don't quite know what we have for a pH, but we're going to be able to calculate that by 3 o'clock. It's exciting, right? Cliffhanger. Here's another question for you, number 15 from the book. Can you have a negative pH? Think about it.
Yes.
Try plugging it in. Try plugging it in. Do you have this? Your AP formula sheet? In the equilibrium box, on the right side. The 7th row, or 6th row, sorry. The 6th one on there says pH equals negative log of hydrogen ion concentration. Yes, we did that last year. Yep. Okay, here's a little sneaky hint. Last year, every single pH that we made you do was a strong acid or a strong base. Every single one. Because if you ask about weak acids and weak bases, all bets are off. We've got to do a little bit more math. So, going back to this question, plug in something. Plug in something for your hydrogen ion concentration. Can you make that pH negative? Did anyone get a negative pH? Just messing around? Okay, so, yes, you can have a negative pH. Okay? Typically, when you think of pH, you think about 0 to 14. That's the range you normally hear. Okay? It's kind of a crock. You can have negative pHs. You can have pHs over 14 as well. All right? Now, having said that, 99.9% of things fall within 0 and 14 for a pH. Okay? The things that don't are highly, highly concentrated strong acids and highly, highly concentrated strong bases. So, everything we deal with in this class and all the examples we use will have pHs within that range, 0 to 14. But it's important to note that it's not completely capped at either end. 0 to 14 is the general range for 99.9% of things, but you can have a negative pH. You can have a pH over 14. All right? So, for example, Carissa, what did you say? Okay, so pH equals negative log of the hydrogen ion concentration. And again, that's where your AP sheet. Okay, this is in your formula sheet. And you plug in a concentration of hydrogen greater than 2. pH is going to be negative. If you plug in 1, I think it's 0. Is that correct? A concentration of 1. So I guess it'd be a greater than 1. Right? So 1.1, if you did 1.1, you'd be negative something. Some tiny little decimal. Okay? All right. Let's introduce ice tables. Ice is an acronym. ICE is an acronym. Okay? And it's going to be a tool. It's a tool that we're going to use to help us solve for the pH of weak acids and weak bases. Okay? I stands for initial. C stands for change. And E stands for equilibrium. Okay. Last year they started calling them Rice tables. The reason is the very first thing you should write down is a reaction. So, if you want to call them Rice tables, that's cool. If you like ice, that's fine. But we do need a reaction for everything we do with an ice table. Otherwise, it makes no sense. We need some context. So, the question here is asking us to prove why the pH of water is 7. So, I'm going to walk you through it. Okay? We're going to use the auto-ionization of water reaction, which is, again, H2O plus H2O It's going to give us that. Okay, we've seen that a couple times now, I think. It was in the homework. And I think I showed it once last week as well. All right. And we're going to use this table and we're going to fill it in. Now, ice tables are using concentrations. So we're looking for the concentration of our pieces. Joe? Because I did it wrong. That's why. Thank you. Let's try that. Thank you, Joe. Let's try that. So we're going to use the ice table to fill it in based on our concentrations. Now, water is a liquid. We don't have to worry about the concentration of water because we can't make a solution of water within itself. Water is just water. So we don't even have to worry about water at all. We're going to skip it completely. Okay? Initially, in this reaction, before we've reacted anything, what's going to be the concentration of these two things? We haven't reacted our waters yet. What's the concentration of these? So don't overthink it. 0. We don't have anything. It hasn't occurred yet. So that's 0. That's 0. The change step in an ice table is going to be variables. We're going to introduce variables. So we're going to use X. So when these break apart, or when these waters react, we're going to get some amount of hydronium, we're going to get some amount of hydroxide. Would we get different quantities for these two? Would we get different quantities for those two? If I react 2 waters, am I going to get 2 of those and 1 of those? Or 2 of those and 1 of those? No, we're going to get the same quantity, right? The ratio is 1 to 1, so we can use the same variable for both of them. I'm going to use X. So plus X, some quantity we don't know yet. Plus X, some quantity we don't know yet. But it's going to be the same. Because for every one of those, I'm going to get one of those. For every hydronium, I'm going to get a hydroxide. Okay. At equilibrium, we write down our final chunk. Okay? Our initial plus our change, that would give us our equilibrium. Now, we had nothing, so these are just both going to turn into X. Okay. This will make a lot more sense why we have to rewrite it when we have a more difficult problem. But for this one, we just have X for each of these. Now, look at your AP formula sheet. All right. In that little box, there's some KW expressions. I think it's the 5th one down. We've got 3 things that KW equals. KW, first off, is a constant. And it's 1.0 times 10 to the negative 14. What else does KW equal? What else do you see there? Okay, the concentration of hydrogen ions multiplied by the concentration of hydroxide ions. Oops. Don't mind me. I'm out of space. Okay? And then there's also Ka multiplied by Kb. We learned that last week. We had used that one last week. We don't need it here. This is the one I want here. We can set up an equilibrium expression for this reaction. Products over reactants. Right? Products over reactants. So, Kw, in our case, in our reaction, the way we have it written, is going to be products, H3O, OH, over nothing, because water is just water. So we don't have a reactant that we're going to include. We're just going to have this. All right? We know Kw is 1 times 1.0 times 10 to the negative 14. Oops. And that's going to equal what we have at equilibrium. At equilibrium, hydronium ions equal X. Hydroxide ions equal X. We have to solve for what that concentration is going to be. So we have X squared. Okay, not 2X. We're not adding these. These are getting multiplied, so it is X squared. And then we can solve for X. All right? We're going to take the square root of both sides. And X is going to equal 1.0 times 10 to the negative 7. So we just solve for X. We just solve for what the hydronium ion concentration is at equilibrium, and we solve for what the hydroxide ion concentration is at equilibrium. They're both the same. We've got this equals 1.0 times 10 to the negative 7, and oops, screwed up. What's the equation for pH again? Okay. Hydrogen ions, hydronium ions are the same thing for our purposes, like I've said. So we can use that. That's the concentration. That's what we plug in. pH equals 7. pH equals 7. Proof. Okay. So that was our very first ice table. We do a lot of ice tables this year. And you'll get pretty good at them. And I guarantee you, you will have to do it on the AP test. I am 100% positive you will see one of these on the AP test. Okay? So, they're kind of important. They're kind of a big deal in chem. You use them a lot. What I'd like to do now is grab that beige sheet you grabbed on the way in. Let's look at that top example. It's titled More Ice, Please. So I know you want more ice. Always, yes. All right, so let's get away from water, and let's see if we can calculate the pH of a weak acid. Like I said, last year when we made you find pHs and POHs, the things we were looking at were always strong. We were always giving you HCl, or we were giving you sulfuric acid, or we were giving you, I don't know, perchloric acid. Okay, you didn't notice it last year because you didn't know. But all the pHs we made you solve last year were strong, because that's easy. Okay? Weak acids are a little different. We have to consider how much of it's going to break apart. We have to look at the Ka value to figure out what our pH is going to be. I'm going to extend this. We've got to set up an ice table to figure this out. So, or a rice table. Again, if you want to write rice, that's cool. We need our reaction first. We're looking at hydrofluoric acid. So we're looking for the dissociation of hydrofluoric acid as our reaction. HF. That's what we got. Again, if you include water, that's perfectly fine. The only difference is you're going to get hydronium instead of hydrogen. Okay? The only difference. Our initial conditions. What goes into ice table are concentrations. Okay? These are all concentrations when we fill in our ice table. So, what's the initial concentration of our hydrofluoric acid? 1.08 molar. What's the initial concentration of my hydrogen and my fluoride? 0. We haven't reacted it yet. We haven't broken it apart yet. Okay. Change. The change. I'm going to lose some quantity of hydrofluoric acid, and I'm going to gain that exact same quantity of hydrogen ions and fluoride ions. Your brain doesn't like it. So, let me give you an example. All right? If I break apart three hydrofluoric acid molecules, how many hydrogen ions am I going to get? 3. How many fluoride ions am I going to get? 3. If I break apart 10, I'm going to get 10 and 10. If I break apart X, I'm going to get X and X. So yes, it looks a little weird, but this is about ratios, not about, this isn't 2x. Okay, this isn't 2x. That's what I'm trying to show you right now. This is correct. It's just whatever quantity you break apart, you will get the exact same quantity of each of these because we're splitting this in half, right? We're breaking it into its pieces. So 5 of these, 5, 5. 10, 10, 10. X, X, X. That is correct. All right? That's our change. Now for our equilibrium, we combine those two steps, and we end up with our initial minus X, and just X and X. Okay. That's our ice table. With the water example, when we set up our ice table, we needed our kW. We needed to use that 1.0 times 10 to the negative 14th. With hydrofluoric acid, what do you think we should use for the value? The Ka of hydrofluoric acid. The Ka of hydrofluoric acid. That's what we need. All right? Does anyone have that offhand? Nice. Oh yeah, that's right. I put it on your sheet. Last year it wasn't on the sheet. I put it on the sheet this year. Making sure you know how to read digits. Okay? That's the Ka of hydrofluoric acid. We have to use that and set up an equilibrium expression with the pieces from our ice table now. So we're going to take 7.2 times 10 to the negative 4th is equal to products over reactants. Okay? So I'm going to write it two ways. I'll show just the normal Ka. All right, we've got H1 plus, we've got F1 minus, and we've got HF like that. But numerically, or what we plug in, is going to be the pieces from the equilibrium chunk. So this is going to turn into 7.2 times 10 to the negative 4th equals x squared over 1.08 minus x. Okay. Now, if you have a nice big fancy calculator, you can solve for that. And if you don't, I'm going to introduce something that I call math magic. And no, that is not an accepted term. That is a Brazen term. But if you ask last year's kids about math magic, they'll know exactly what you're talking about. Okay? So let's do a little math magic. If you try to solve for x normally right here, it's a giant pain in the butt. You got to reorganize it, and you need to do a quadratic. X equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a, whatever it is, okay? Remember the jingle? Pop goes the weasel. Inspire. Okay, if you have an Inspire, it'll do it for you if you know how to plug it in. However, for non-Inspire folks, here's what you can do. Here's what you can do. You can do that. You can get rid of the x in the denominator. Well, we don't have to. Yeah. So if we get rid of the x in the denominator, and now solve for x, it's much easier. Okay. What we have is this gets multiplied over here. Then we just take the square root, and we've got x. So why don't we do that? Somebody do that really quickly. Move the 1.8 over, multiply it by 7.2 times 10 to the negative fourth, and then take the square root of that. Let me know what you get for x. That's math magic. I'll explain it. This is what I'm getting at. This blew the kids' minds last year, but I'll show you why it works. I'll show you why we can do it. Did anyone solve for x this way? Did anyone do that? I'll do it. Okay, 0.027.
Yes.
27885. So 28.
Well, actually, yeah.
Okay. So we get an x of 0.28. Drew, when you used your solver, what did you get?
Negative 0.028.
Or?
0.0275.
So 0.028. So, if you include that x, and you use solver like Drew just did, we got 0.28. If you get rid of that x, and you make it nice and easy, we get 0.28. Or 0.028. It's a little off. Sure. But it's statistically irrelevant.